Welcome to this MOOCE course on plastic working of metallic materials. Today I will start with the first lecture, that is the introduction of plastic working of metals. See, all man-made objects which we use daily are obtained by some sort of manufacturing processes, and these objects now consist of assembly of a large number of parts. If you take any of this object which you are using daily, it will consist of a large number of parts. So, for example, an automobile part itself consists of more than 15,000 parts of various components, and each of these components are manufactured by different techniques. So, like even with the connecting the car frame body, so the body itself consists of different parts. The chassis is there, the wheels are there, the axle is there, the steering system is there, suspension system is there, brake system is there. So, you will find that it consists of more than 15,000 different components which have been manufactured by different techniques. And all these most of these are manufactured by various shaping operations. So, we can say that manufacturing is the conversion of raw materials into finished products employing suitable techniques. Okay. And this manufacturing can be broadly classified into the manufacturing techniques can be broadly classified into casting, where you get the shape, you are taking a molten metal, pouring it into a mold, a shaped mold, and allowing it to solidify. So, and after the solidification you get that particular component, the shape of the mold itself, and then okay, after that you will be doing some other operations. Then another is the metal forming process, in which you will find that say either the material, there is a bulk deformation which is taking place, it is deformed in a bulk, or you will find that sheet metal operations are there. So, if it is bulk forming like connecting rod, crankshaft and other parts, you make it by forging. The different sections of the automobile body parts itself consist of different angle sections, channel sections, eye sections, all these things are there. So, those are made by other techniques, metal deformation processes, and maybe sheet metal operation is there, where you do the sheet metal operations. And another method of getting the shape is the joining technique. Say for example, if you want a bridge, the bridge cannot be made by casting technique or metal forming technique. Of course, there are metal forming techniques to get certain components, the structural shapes, and that will be, you just add on to it. So, that you call it as additive technique. You add on to it by joining, or maybe there are some cladding techniques for obtaining some specific shape, whereas in welding or joining technique, different components are joined together. Maybe it may be a permanent joining or it may be a temporary joining. Permanent joining means you go for welding operations or bracing operations, whereas for temporary joining operations, it is like say fasteners, nuts, bolts, screws, and all these things you are using for the temporary joining operation. So, and finally build up the shape. So, you cannot cast a bridge. Okay. So, that is why this is taken into this by joining technique. Another is powder metallurgy technique, where metal powders, maybe alloy powder can be there, or individual powders are there, and you add the powders for obtaining the specific composition. You are just mixing it thoroughly, blending it, and sometimes you do the mixing technique is there, so that mechanically an alloyed powder also you can get it. The latest trend is that. So, that metal powder or alloy powder, you just compact it in a die by means of a die and punch assembly, and then you compact it so that you get a particular shape and with the required dimensions. So, that green, you call it as green compact, these are then taken to a furnace and you do a sintering process. That means you are exposing to a higher temperature for sufficiently long time. So, in that process, during the compaction process, what you got was that individual powders, they were having a mechanical bonding. So, it may not have sufficient strength, only that strength required for handling only you are getting it. In the other case, when you are sintering it, there is a chemical bonding between the individual powder particles of that called compacted piece. and finally you get a uniform composition throughout the structure, and the required shape and the dimensions are obtained, and you will find that this technique is used for some special cases where other techniques may not work, like say casting you may not be able to obtain it. The advantages are that in casting you may find lot of segregation and coring which are coming, plus other casting defects may come into picture, and so you may not have a proper control of the grain size, whereas in powder metallurgy components you have a proper control of the grain size, a homogeneity in the composition you can get it, and all those things comes into picture, but that is a powder metallurgy technique. So you can get, especially when you wanted smaller components and large, then powder metallurgy is the solution for that. Another is the material removal, or you call it as the machining technique. It can be the conventional machining technique. From the bulk material you remove the materials so that you get the final shape, but in this lot of losses are coming into picture. And say this consists of say traditional machining techniques like machining it in a lathe, a shaper, or a milling machine, or other techniques, say drilling, so then you have broaching, you have the planer, so all those things are there, you can get the final shape. Or you have the non-conventional technique specifically which is useful for some specific materials, say like electrochemical machining, electric discharge machining, laser machining, okay, then electron beam machining, chemical machining. So, all those things are there which comes under the material removal. In this case material loss is there, sometimes if it is a costly material one cannot afford the loss of material. Okay. Now, the last case is the special processing and assembly technology, which are the evolving or developing technologies which are being used, and some of the examples are say semiconductor devices, micro electromechanical devices. So, nowadays the latest trend is the NEMS, nano electromechanical devices, and other things. People are putting a lot of effort into this. So like special processing and assembly technology has been developed recently, and some of other examples are the 3D printing, rapid prototyping, lithography technique. These are the emerging trending, those are the special processing and assembly technology. And with this, so I have already mentioned all these techniques here. When you come to, because this course is basically for metal forming or plastic working of metal, which comes under the metal forming process, let us look into the classification of the metal forming processes. So, metal forming is nothing but a large group, it consists of a large group of manufacturing process in which the final shape of the metallic workpieces are obtained by plastic deformation. It is just by plastic deformation. By plastic deformation processes in which the volume and mass of metal are conserved and the metal is displaced from one location to the other. During deformation, whatever be the material, there is a shape change. So, metal moves from, it displaces from one place to the other, and then you get the final required shape. Okay? But there is not much loss of material in this. And another method is by metal forming is the metal removal or machining process, in which material is removed in order to give it the required. These two are broadly classified as the metal forming process. So, this course will be mainly concentrated on the deformation processing or plastic working of the metal. So, during creation of useful shape by plastic forming, the mechanical properties are being controlled. So, when you are going to deform the material, you will find that the properties of the material changes, because many times it improves. There may be defects in the bulk material in the as received form. Maybe like if you are having a casting technique, the primary processing was casting technique, and in that you may have a lot of blowholes, lot of inclusions and other things, by which the strength of the material may be reduced. So, but during plastic deformation these are minimized. We cannot tell that completely eliminated. Say for example, when you are subjecting it to deformation, the blowholes or pinholes or any other gas defects, okay, which are there inside the material which was formed during the casting techniques, they get cold welded. So, you say that it is eliminated, though it is 100% not eliminated, and say maybe inclusions are there, it may be broken up into fine second phase particles and distributed. So, all those things comes into picture during the deformation. So, by which the mechanical properties gets increased. See, and now when you are deforming the material, there is something called as preferred orientation. So, metal deforms along certain particular crystallographic direction, and in that case you will find that anisotropic properties are coming into picture. The material after deformation, you will find that the properties are increased along or improved along certain particular direction, and maybe with a concomitant decrease in the other directions. So, that is there. So, one has to look into the direction of metal flow during the deformation. The mechanical properties are controlled by say strain rate, the temperature, direction of the metal flow during the deformation, etc. During the plastic deformation, there is a chance, depending upon whether it is done in the hot condition or in the cold condition, there is a chance that refinement of grains can take place. And when there is a grain refinement, it increases the yield strength of the material. So, those type advantages are there during the deformation processing. So, when you classify these plastic working processes, you can classify it into depending upon the nature of stresses or type of work which is being done. So, you have that some of the majority of the plastic working consists of those techniques where the process undergoes the material undergoes compressive stresses. So, like a compression type process are there, then indirect compression process are there. You may not be applying a direct compression stress, but you may be applying a tensile stress, but between the workpiece and the die material there is going to be compressive stresses. Then tension type process are there, generally which is the sheet metal operation, bending process, bending operation to get a particular shape, shearing operation where you wanted to shear the material. So, these examples are direct compression type. A simple example is a forging, the open die forging between or closed die forging between two dies. The workpiece material, the shaded piece is the workpiece material which you will see here, that is being compressed between two platen. Maybe inside this die, if you give a shape and you are just compressing it, the metal will just flow. Maybe you might have seen this small children playing with the plasticine, that clay, and making the models. The same thing, you can just press it, then you will see that the metal pieces just flow, and then if there is a cavity here, it will fill up the cavity, the mold cavity, and then you get the final shape of that. This is a typical example of a forging. Forging itself consists of open die forging and closed die or impression die forging. Now, in this case, so this is a between two roller, you will find that the material passes between two roller. So, the interface between the material and the roller, you will find that there are compressive stresses which are acting on that. So, this is called as the rolling operation. A typical example of the rolling operation is extracting the sugarcane juice on the roadside. You will see most of the in most parts of our country, you will see that. That is a typical rolling operation, but in industrial rolling where you are doing on sheet metal work, these things are different. Okay? But the principle is the same, rolling operation. And another is the second classification is the indirect compression type process. See, for example, there is a die here. Into the die, a converging die is there, and into that you insert a material and pull through the other end. So, you are applying a tensile load here, but you will find that the interface between the workpiece and the die, there are compressive stresses. So, that is why it is called as indirect compressive stresses. So, an extrusion process. Extrusion process is typical. So, this is a typical of a wire drawing operation. Extrusion is every day you are using an extrusion process in your home. The first thing you do is get up, take your toothpaste and press it on the back side, and through a small nozzle the piece comes out. This is a typical extrusion process. Okay. So, here because that is a semi solid part, it is not difficult, but in for your metals, now you may have to apply a stress in this direction shown by this through a piston arrangement, piston and cylinder arrangement, and this is your die. So, between the die, that is an orifice, the metal is forced through this region, but you will find that the compressive stresses are developed on the lateral side of the die, inside the die. And here depending upon the shape of this opening, you get the particular shape of the component which you are getting and the size. Now, another is the deep drawing operation, how you make say maybe a cup and other things, steel tumbler you make it, no, those are by the deep drawing operation. You have a die here, kept it, and then okay, through means of a punch, and at the surface you are just holding it, and through a punch you are just drawing it. Okay, so it will go it. So there are tensile stresses developed it, there are bending stresses developed it, there are compressive stresses developed it, and see this deep drawing operation becomes a slightly complex nature of stresses are there. Then the tension type process, this is a stretch forming. You will see it extensive use in the automobile body parts where you wanted to get the shape. Okay. So, you have a material which is kept here, sheet metal which is kept, and through means of a die you are just pushing it. So, you may get there are tensile stresses are developed inside the material, and you get the shape. The bending process where you are getting a, see here it is showing for a 90-degree bend angle, but you can a very complex contour shape by bending operation you can get it. Then another is the shearing process where you cut the material, shear the material into small pieces as per your requirement. These are all involves this metal forming process, sheet deformation processing technique. Now, you can have classification by subgroups, the metal forming process. So, one is the tensile forming where you have the stretching, expanding and recessing. You have the compressive forming, the examples are rolling, open die forging, closed die forging, indenting. Indentation is another process of compressive stresses, pushing through a die. So, that is the extrusion. Combined tensile and compressive forming is there, pulling through a die, deep drawing, flange forming, we will come to that later. Metal spinning where you are just rotating the workpiece material and then pressing it on a mandrel to get the shape, the inside shape of which will be same as the outside shape of your mandrel. So, that is a spinning operation. Then upset bulging, you are just upsetting it to get maybe a typical example is your nut and bolt operation and other things. Okay. Forming by bending, bending with the linear tool motion and bending with the rotary tool motion, these are two different techniques. Then forming by shearing, joggling, twisting, blanking, coining, these are all shearing operations. So, next is that when you wanted to study about this metal forming, the most important thing you have to study is the mechanics of the metal working, because you have a material and this material has so you should know about what are the relationship between the stress and the strain. When you are deforming, how much the stress will increase. So, your the required load, how much it will increase. Maybe because of that at some point for the defect are forming, you are required to know all these things, and if there is a chance that defect is going to form. So, in that case you have to stop it at some point, do some other process and again come back. So, maybe a process you call it as annealing, intermediate annealing, and again come back. So, you should have a very clear cut knowledge about the stress strain relationship or the material behavior under various conditions. These are the most important thing. So, the metal working occurs due to plastic deformation which is associated with the analysis of complex stress distribution, and this requires simplification. Only large plastic strain is considered. See, when you look at the stress strain relationship between any material, when you are looking into that, one thing is important, that is as from the point of view of a design engineer is interested only in the elastic range. That means where the strain is very small. So, his limitation is it is the point at which the metal starts plastically deforming. So, he will not go into that level where plastic deformation is taking place. That means the strain is very small. Whereas, for the point of view of a metal working engineer, an engineer working in with dealing with the metal working, then the plastic strain which is considered is very large. If a design engineer is looking at a strain of say 2%, the person who is working with dealing with the metal working operation, the strain may be more than 1 or sometimes 10. In some superplastic deformation case, the strain will be maybe 100 or 1000, it may go to a very large amount also. So, that is there. But in the simplest way, we can say that for when you are dealing with the mechanics of metal working, the strain is large where it is purely in the plastic strain which is considering. So, that is the part where you have to look at it, while the elastic strain, because it is very small compared to the plastic strain, that will be neglected. And when you are working with the real material, the material undergoes strain hardening. That means the more and more plastic working, your yield strength, the stress necessary for further plastic deformation, that keeps on increasing. But for the simplification, when you are looking at it, these are the things: elastic strain you neglected, the strain hardening often neglected, but finally at the end you will again introduce it back. And most of the cases is the metal is considered to be isotropic and homogeneous. This is the case where you start with, but later you may come back to the case where it is non-homogeneous or isotropic and other things. So, these are the simplifications which people go for when you are discussing with the mechanics of metal working. In actual situation, plastic deformation is not uniform, that one should understand, and also have friction which is coming. Friction which is coming due to internal friction, it results in the strain hardening. The friction which comes as a result of the interaction of the workpiece with the die or the tool. So, that also comes, this also increases your stresses required load. Hence, the need to simplify the stress analysis in order to determine the force required to produce a given amount of deformation for the product with the required shape and dimensions. This is required. So, when you look at the cases, certain cases, we will come to that part, the relationship between the stress and strain, but let us say that the other simplifications are for plastic deformation, always you assume a constant volume relationship. The volume of the material remains same, maybe with an initial height of H0 and a diameter H or D. When you are compressing it, its height decreases, but then you assume, then you will find that the diameter keeps on increasing. So, the volume at the initial and the final stage remains constant. This is another assumption, and in such case the three components of strain, the sum of the strain components epsilon 1, epsilon 2 and epsilon 3, this is equal to 0. This is the first assumption of constant volume, this is the assumption of constant volume relationship. And in metal working processes, you will find that majority of the case, it is the compressive stresses and strains are being used, most of the operation when you look at it. So, if a block of initial height is compressed from H0 to H1, the axial compressive strain will be, you can find that this, we will come to that soon, the strain is minus log H0 by H1, where H0 is greater than H1, where H0 is the initial height of the material. So, in engineering strain, so this is the true strain, this is the engineering strain, you can get it as H1 by H0 minus 1. But when you are discussing with the stresses which are compressive in nature, you will find that these strains are taken as negative. So, convention is reversed in metal working problem, so that the compressive stresses and strains are defined as positive. Okay. So, you define it as positive and then you do the analysis. Only thing is that it does not matter whether it is compressive or tensile. What matters is what is the amount of strain you have given in plastic working of metal. That is why. So, there is not going to be much. Only thing, when you do the calculation, you have to be very careful what you are taking it. So, that way compressive strain you are getting as log H0 by H1. So, this is, in the other case it was H1 by H0, and here it is 1 minus H1 by H0. And the fractional reduction in metal working, this is another parameter which people takes case, is that R is equal to this defined by A0 minus A1 by A0. And from the constant volume relationship, you can always relate this fractional reduction in terms of strain as this, or A1 by A0 is equal to 1 by R, and the strain epsilon, that is related to your fractional reduction as log 1 by 1 minus R. This relationship you may very often encounter when you go during the this one. Now, how to have the relationship between this stress and strain for the material, because whatever you are going to do, you should have a thorough understanding of the behavior of the material when you are subjecting it to plastic deformation. So, you should know the information which you can obtain, is by a simple tensile test or a compression testing. A compression testing, you take a cylindrical sample, press it the way we have shown it, and finally after some amount of strain you get the measure the load and the strain, and then you can get the relationship. But it is very often convenient to get more information in a tensile test, because when you are deforming the material will not fail under purely compression. This is a general rule. So, the material, when it is subjected to say some sort of stresses, it will fail when there is somewhere some tensile stresses are developed. Then only the internal defects will start forming, and then the final failure will take place. So, the best thing, the simplest thing which people look at is to conduct a tensile test. Now, let us discuss about how the tensile test is done, what are the information we can get it, and how you can analyze the tensile test result. So, standard tensile test is based on a physical problem, where a thin rod is pulled axially. It is pulled and subjected to tension. Okay. The corresponding, so in that machine when you are pulling it, what is the load which is required for the pulling? You are measuring it, and so that is that load required, the corresponding load is measured. But when you are doing this tensile testing, the basic assumptions are the load is purely axial, there is no bending and other things or a combination. So, you have to have your specimen in such a way that there is only axial stresses. Okay. Then deformation takes place uniformly along the length. So, the uniform deformation is taking place. So, if the length is increasing, correspondingly for maintaining the uniform deformation, you will find that the diameter is decreasing. So, decrease in the diameter also is uniform. Okay. So, across any section when you look at it, the diameter should remain constant at any point. So, that means deformation takes place uniformly along the length and along the cross section. The quantities to be measured during the tensile test are: 1, the load by which you are applying, because you are subjecting it to a strain, and when you are pulling it, what is the load which is coming, what are the stresses which are developed, that is what you wanted to find out. So, the quantities to be measured are load and extension of the specimen across a known length. When I am pulling it, if I know the dimension, a known length, and then how much it is expanding when you are pulling it, that is the extension, you can measure it. These are the only two parameters which you are going to measure when you are conducting a tensile test. For conducting the tensile test, you have different specimen, but generally people use two types of specimen, though non-standard specimens are also there. One is the round bar for measuring conducting a tensile test on a bulk sample. Okay, round cylindrical type thing with a reduced cross section at the middle, and another is flat specimen for the sheet products. So, this is the round bar, say a uniform round section is the cylindrical piece is there. At the center portion you have a reduced cross section with some radiuses are given. As per the ASTM standards, you can get the standard dimension for this. If you are, when you are conducting a test, you follow some standards. Generally throughout the people follow this ASTM standard, though in European countries they also have different standards and other thing, but more or less the principles are same. And if you are having a sheet metal work, you have a flat specimen, say from a rod you just cut it at the middle, there is a reduced section. Okay. And these two parallel sections, these are parallel pieces. So, you can see from here to here there is a parallel length, here also there is a parallel length. On this you can just clip an extensometer of known length, you call it as a gauge length. Of known gauge length you fix it, you attach it to that, and then finally what happens is that during the testing that distance keeps on increasing and you can measure the extension. So, the terminology which is used are stress defined by nothing but the external load P. So, here when you are pulling it, so you can just pull it here by load P. So, this P by this cross sectional area maybe at any instant, that is called as the stress, that is defined by the stress, and almost all of you are familiar with the definition of stress. So, I am not going into that. Another strain is that change in the length. Say if the distance was here and after loading when you are pulling it, there is a displacement in the length. So, that displacement, the extra displacement is the delta L by L naught, which we can write in the integral form as 1 by L naught integral over L0 to L dl. When you are doing a test, what are the measurements you are doing? You are measuring the load and you are measuring the displacement. You know that initial cross sectional area of the sample, the initial gauge length you know. Once these two things are there, you can find out the stress and the strain. Okay. In terms of the initial cross sectional area, if you are measuring, then you call it as the engineering stress, defined as S is equal to at any instant where P is there divided by initial cross sectional area. So, that is the engineering stress. Why it is called as engineering stress is because it is importance only for a design engineer, okay, where his stresses are not going to a value beyond the elastic limit. Okay. So, it is much below the Young's modulus value of the material. And so, engineering strain also, the change in length per unit initial length, gauge length, that is what E given by this relationship. That means change in length, the delta L is nothing but L minus L naught divided by L naught, where L naught is the initial length, and so you can write it as that instantaneous value for any value of L. So, that is the E value we can calculate by L naught minus 1. So, this is how you get a typical stress strain curve. So, in this, when you look at it, what you can see is that initially there is a linear path. So, this load versus elongation, if you are plotting it, you will get the same type. Only thing is that here the stress divided by area and the strain by delta L by L when you are doing it, you will get this type of a plot. Initially, this is a typical engineering stress versus engineering strain plot. So, where this L should be, L naught should be here. So, initially you will find a linear path, the curve is very linear, it obeys a linear relationship, that is stress is proportional to strain, the famous Hooke's law. Okay. So, in this region you have the this is called as the elastic region. So, when you remove the load from any point in this region, maybe from 0 to 2, when you are unloading it, when you remove the load, it will again come back to the initial length. So, that whatever extension took place, that becomes 0 the moment you remove the load, that is what. So, that is the region of elasticity. Now, it is not easy to find out which is that point at which this elastic limit is reached, beyond which certain case no, it will not come back to the initial position. So, there is a very difficult, there is a very tricky situation. So, for that case from 0 to 1, the material behaves in a linear way. So, that is the region of linear elastic region, and the slope of this stress strain plot in this region is nothing but your Young's modulus value of the material. Now, from here, so up to this point when you remove it, it will come to the 0 position, there won't be any displacement, and still you increase it, it is no longer linear. There is some amount of non-linearity comes into picture. So, linearly it should have gone like this, but here it is moving along this line, say from 1 to 2. But still, till it reaches the point 2, you will find that when you remove the load, it again comes back to the initial position. So, that means there is no permanent extension which has taken place, or permanent deformation has not taken place. But at some point, you will find that if you remove it, a small amount of permanent deformation has set in, metal has deformed plastically, then you call it as. But it is very, very difficult to know, and conducting a test, say loading, unloading, loading, unloading and other things, that depends upon what is your step jump. So, it becomes very difficult. So, generally what people do is that you just keep on loading it, and then you draw a line parallel to this initial slope of this line with a strain of 0.2 percentage or 0.002 of your gauge length. So, that is 0.2 percentage strain. You mark a point and draw a line parallel to the initial slope of the line. Wherever it meets, you get the 0.2. This is called as the offset strength or 0.2 percentage offset strength. This is the normal method of determining the Young's modulus, yield strength of a material. This is under the assumption that any component, when say a strain of up to 0.2 percentage, a permanent strain of up to 0.2 percentage is can be accommodated without changing much of the performance of the material. So, that is under that condition, that subject to that condition only people are taking this yield strength as this one, because it is very difficult to find out at what exactly at what point the deformation has taken place. So, this is the thing. So, initial linear portion is the elastic region where it follows Hooke's law. Since accurate determination of elastic limit is very difficult, it is often replaced by a proportional limit. The slope of the stress strain curve in this region is defined as the modulus of elasticity. So, all those things are. Now, from point 2, when you increase it, you will find that the yield strength keeps on increasing. So, from point 2, the yield strength keeps on increasing. So, when you unload the specimen at any point beyond 2, you will find that there is a permanent deformation takes place, and with the more and more straining, this permanent deformation keeps on increasing, because initially whatever was the elastic energy absorbed, that will always remain constant. But you will find that the stress necessary for plastic deformation, that keeps on increasing with the increase in strength. So, that means the material undergoes strain hardening. Okay. So, the strain hardening is nothing but the increase in the yield strength as a result of the previous plastic deformation. It keeps on increasing and it reaches a maximum value at some point. Maybe we can say that in this curve it is at 0.3. Beyond that, you will find that the load keeps on decreasing. So, when the load keeps on decreasing and somewhere at 0.4 it fails, at a lower stress it fails. So, this point, so point 1 is the proportional limit where stress is proportional to strain, Point 2 is the yield strength, where beyond that the material undergoes permanent deformation or plastic deformation, and 2 to 3 is the region of homogeneous deformation. From 2 to 3, when you deform the material deforms homogeneously. That means, with whatever increase in length is there, it maintains a constant volume relationship, the cross sectional area decreases, and entire length of the gauge length, entire section of the gauge length, you will find that the decrease in the cross sectional area is or the cross sectional area remains same across the length. And but at point 3, you will find that instability sets in. The specimen at some area, its cross sectional area decreases. Maybe these are the region where there is a stress concentration, or it may be the region where there is a defect which is there, internal defect is there, so that that results in a stress concentration. Whatever it be, lot of things are. Maybe it may be the region, the minimum cross sectional area, if there is no defect also. Ideally, if you look at it, if there is no defect, but still during the specimen preparation there is some region where the cross sectional area is minimum, it will be at that region, because that is the region of stress concentration. So, at point 3, a necking, a reduced cross section takes place. The phenomena is called as necking, like the neck, is a cross section which is lesser than our body and our head. So, that is why it is called as necking. So, somewhere the necking takes place, and then with the further straining, the neck region, that the deformation starts increasing, like localized deformation takes place, and its cross section area keeps on decreasing, and at some point it cannot withstand the load, and then it fails at 0.4. This is the typical case for a typical engineering stress, engineering strain diagram for a typical ductile material like aluminum, copper, nickel, etc. These are the pure alloys. So, when you are determining the stress and the strain, so whatever we discussed was the initial gauge length and initial cross section of the specimen were taken. So, either A0 or L0 were taken in our calculation. So, P by A naught. So, that is the engineering stress, and delta L by L naught, where L naught is the initial gauge length. So, based on that, that is why we call it as the engineering stress, engineering strain plot. That will give you an idea how much the material can withstand, how much load the material can withstand. That is the best idea for the information which you can get it from that. But as a specimen deformed plastically from region 2 to 3, okay, this is a mistake, from region 2 to 3, the gauge length extension is accompanied by a reduction in the cross sectional area. So, when the cross sectional area decreases, you have to find the exact cross sectional area at any instant, and then the load divided by that instantaneous value of cross sectional area, you have to take it. So, the actual stress sigma across the cross section is therefore higher than the engineering stress, and the true stress, that is the actual stress, that is the true stress given by sigma. So, remember, S we will be using for engineering stress and sigma for the true stress. Similarly, E for the engineering strain and epsilon for the true strain we will be using. So, the true stress is given by P by A. So, in plastic deformation the strains are usually large, hence the strain is represented by the term true strain or natural strain, because the deformation is very large, that is epsilon, which is the ratio of change in length referred to the instantaneous length instead of the original gauge length. Okay. So, that is what we are telling. So, if you just take it for each deformation which is taking place, maybe from starting from L naught it has deformed to L, then what is the strain increment there? So, that is what you have to do. The total strain will be the sum of these strain increments, which is given by like this sigma over L1 minus L naught by L naught plus L2 minus L1 by L naught. So, at instantaneous strain you have to calculate it, instantaneous length you have to calculate, or cross sectional area you have to calculate it and then find out. So, this is the sum of all the strain increments is the total true strain which you call it. So, in integral form you can write it as epsilon is equal to integral over L naught from L naught to L dl by L, that is equal to log natural log L by L naught. So, true stress is given by this relationship, which we can write it as sigma is equal to P by A is equal to P by A naught into A naught by A. You can find out the relationship between what is A naught by A. So, that is, if you are assuming the constant volume relationship, A naught by A naught L naught is equal to A into L, where this is the initial cross sectional area and the initial length, whereas A and L is the instantaneous cross sectional area and instantaneous value of the length, gauge length, due to the expansion. So, from this you can find out A naught by L is equal to L by L naught. So, that is from our relationship earlier with E, you will find that E is equal to A naught by A minus 1. So, from that we can write that A naught by A is equal to L by L naught is equal to E plus 1. So, this A naught by A, if you substitute here, you will find that the true stress relationship is given by sigma is equal to P by A naught into E plus 1, that is given by P by A naught is your engineering stress into engineering strain plus 1. So, that is what the relationship between true stress and engineering stress in terms of your engineering strain, you are getting it. Similarly, engineering strain is given by E is equal to delta L by L naught, that is L minus L naught. From that you will get this relationship. From this it implies that E plus 1 is equal to L by L naught. So, this epsilon is equal to log L by L naught. So, we can write it as L by L naught is nothing but E plus 1. So, you get this epsilon is equal to E plus 1. So, these two relationship, how to determine the true stress and the true strain in terms of engineering stress and engineering strain, you can easily get it by this relationship. Now, this is a common stress strain axis I have taken, but if you plot the engineering stress strain curve and the true strain curve, you will find that it is different. In the true strain curve, because of the necking, you will find that localized necking is taking place. The cross sectional area at that point of necking is very less, so there the stresses are increased. Though your external load is decreasing, that is because of the reduced cross sectional area. So, you will find that the true strain plot will be this, and whereas the engineering stress engineering curve will be like this. After the ultimate tensile strength or maximum load is attained, the engineering stress engineering curve will show a dip or reduction in the stress value with the strain till it fails, whereas true strain curve, we are considering the actual cross sectional area, you will find it continuously keeps on increasing till failure. So, advantages of using the true strain are that we will do some problem and then you will understand it. The values of true strain is not dependent on the nature of the strain, that is whether it is tensile or compressive, and depends only on the initial and final size. If I just have a piece like this, and I just elongate it into double the size of this, calculate what is the stress, the engineering strain and engineering strain for these two from say maybe L naught to L, maybe if you are just doubling it, just assume maybe 50 mm to 100 mm if you are increasing it. So, calculate the true stress and true strain and engineering strain. Now, again you deform it, compress it back to the original shape, and then you find it out. You will find that if you are doing this total strain by engineering strain concept, you will find that the strain there is some value. But when you are taking the true strain concept, because reduction in the length you are considering it as compressive in nature, so there the sum of these things will be 0. So, that is one thing. So, total true strain is equal to the sum of the incremental strain, that also is there. So, maybe from 50 to 100 when you are going, from 50 to 60, 60 to 70, 70 to 80, 80 to 90, 90 to 100. In each case you calculate from 50 to 60 what is the length. So, from engineering stress strain point of view and true strain point of view, you just calculate it and do that sum of the strain increment. Then you will find that the total strain from 50 to 100 is equal to the sum of the strain increments when you are using the true strain concept. But if you are using the engineering strain concept, you will find that total strain is not the sum of incremental strain. Okay. So, that is the thing. So, these two advantages are there, but in any case when you are dealing with the plastic deformation of the material, this true stress true strain curve is called as the flow curve. So, you call it as flow curve. This is very much important for plastic working of material. The reason is, in this, if you know how much amount of strain the material has been subjected to before you got it, you can understand that if you know the relationship, you can really find out what will be the the yield strength of the material. Yield strength will keep on changing on the flow curve depending upon the strain. So, if you are buying the material from the market and saying, and your supplier is telling, okay, this is the material after annealing, it is subjected to a strain of 0.2 or it is subjected to a 0.5, then you can find out what will be the exact yield strength of the material. So, that will keep on changing, that is one advantage. Or if you get a material, the material is known to you, and then you find that okay, its yield strength or some value, then if you have this stress strain with you, you can find out how much amount of strain has been given to this material before you used it or before you received it. Okay. That is the advantage of this. So, at any instant of time or when you are deforming, as I mentioned earlier, the deformation will not be homogeneous at different sections, the amount of strain may be different. So, you can find out at which section the maximum strain will take place, and that is the point where you have to concentrate, so that failure will not take place. So, all those important information you can get from this flow curve, and for the kinetics, for studying the deformation behavior of the material, this true stress true strain curve is more important. And there are various ways of representing the stress strain curve, we will come to that later. But in this we found that ultimate tensile strength where the maximum load is there, you have to calculate, you wanted to find out the relationship between this the true stress at maximum load. So, ultimate tensile stress is given by say SU given by P max, what is the maximum load by A naught. Then the true stress at maximum load sigma u is the P max by AU, where you should know what is the initial cross sectional area. Also you know that the strain at maximum load is log A naught by AU. So, from the above relationship you can find out, see if you substitute into this, we can get this epsilon u is equal to SU into A naught by AU, or epsilon u, the true stress at maximum load is nothing but SU into say E raised to epsilon u. Now, another thing which you have to consider is that we discussed after reaching the maximum load, the cross sectional area decreases at some localized area, and at that localized region the plastic deformation is very large. So, there is no longer the material is deforming in a homogeneous way. So, what happens is that there is an instability in tension. So, instability in tension we have to find out. So, once the stress has reached a maximum value, the engineering stress strain curve shows a decrease in the stress value with the strain. This region is accompanied by necking, which generally occurs at regions of stress concentration due to the maximum cross sectional area or presence of defects. In real materials, during homogeneous deformation, it undergoes strain hardening, thereby increases the load carrying capacity of the specimen due to plastic deformation. So, on one hand, you will find that the material undergoes plastic deformation. So, there is it undergoes strain hardening. So, because of the strain hardening, the stress necessary for further deformation increases. But other hand, you will find that the cross sectional area of the specimen keeps on decreasing. When the cross sectional area keeps on decreasing, the actual stress keeps on increasing. So, that means these are two opposing factors. The load carrying capacity it increases, and that it is opposed by the gradual decrease in cross sectional area of the specimen. So, localized deformation begins at a maximum load. At this stage, increase in stress due to diminution in cross sectional area of the specimen becomes greater than the increase in the load carrying ability for the metal due to strain hardening. So, the condition of instability is there. At maximum load, you will find that the change in load is 0, that is dP is equal to 0, that is the condition for tensile instability, and you know that P, the external load P is nothing but stress into the cross sectional area, instantaneous value of cross sectional area. So, that means in writing in the differential form, you can write that dP is equal to sigma dA plus A d sigma, and since the condition of instability onset of necking is equal to 0, you equate it to 0. So, but from the constant volume relationship, we already get this relationship dl by, sorry, this should be dl by L, somehow this has L and dA by A is equal to d epsilon. So, if you substitute into this, you can get dA by A is equal to d sigma by sigma is equal to d epsilon, or it implies that finally you arrive at d sigma by d epsilon is equal to epsilon, a condition for tensile. That means, if you are loading this, if this is your true stress true strain curve or your flow curve, and then you find out the d sigma by d epsilon, taking that function and then you start plotting with versus epsilon, you will find that when it reaches at any point where the d sigma by d epsilon is equal to 1, that is the point the strain at which this takes place, and your stress at maximum load will be based on that. So, that is how you calculate. So, here this is the point at which you will find that d sigma by d epsilon is equal to sigma. So, from this true stress true strain curve, the point of necking at maximum load can be obtained by finding the point on the curve where the subtangent is unity, because if this was your curve, flow curve, so you find out, you draw a subtangent at which from there it is meeting this strain axis at 1. Okay. So, that is what. So, that is the point at which, but it is very difficult to exactly find out where it is. You have to keep on doing a little bit of iteration, and then only you can get it by physically measuring it. So, that becomes very difficult. So, instead of the true strain curve, if you just take the engineering strain, then we can express the necking criteria as d sigma by d epsilon is equal to, you can write it d sigma by dE into dE by d epsilon. So, that you can write that this relation, and this is equal to dl by L naught by dl by L. So, that is equal to, you can finally get this relationship d sigma by dE into 1 plus E, that is equal to sigma, or d sigma by dE is equal to this relationship, that is equal to your true stress divided by 1 plus engineering strain. So, that is the condition for this. It is called as the considered construction for the point of maximum load, the true stress versus engineering strain. So, when you just to plot that true stresses, instead of true strain, you plot the engineering strain, then it becomes easy. From that point 1 plus epsilon, you know, it will give you the value. From there, if you draw the plot, you can find out the stress, the maximum stress, or the point of instability, that is the point of necking, or point of plastic instability, you can always find it out from that point, which we will be discussing in the next lecture.